Okay, I'm here to present to you carbohydrates. Everybody loves carbohydrates. It's basically our favorite thing to eat as a human species, as we are as animals. And the reason for that is because carbohydrates are full of simple sugars. They break down super easy into the human body, and we can utilize the energy from them almost immediately. We actually start breaking down carbohydrates in our saliva. We have an enzyme called amylase. So the second you put a carb in your mouth and you start to chew and mix it with your saliva, you're actually already breaking it down and possibly absorbing a little bit of the carbs through your mouth. Then, of course, the intestines do the rest of the absorption. Human beings, as animals, tend to drift towards quick energy because there was a time in our evolution very recently for us that we needed to be able to sprint and run and get away and chase down prey. We are something called persistent hunters, which means what we do is instead of aggressively chasing down our prey, or historically speaking, we actually just stalk it for days. We don't slowly walk, but we just stalk the prey for days, and the prey runs and runs and runs and runs, and we just keep approaching, and eventually it gets so exhausted it can't run anymore. It's actually a terrifying way to hunt if you think about it, if you are the prey animal. So we tend towards quick energy, so we love our carbs. I'm gonna make me go away. Okay, so carbohydrates are the pastries and the ice cream and the breads and everything. What we should show here is the fruits, the actual fruits of the planet, oranges and guavas and pineapples and papayas and all those wonderful things, because that's natural sugar, which was the only thing we had available to us for a very long time in terms of simple sugars. When we started processing sugar, that's kind of where everything took a turn in terms of health, because processed sugar, it turns out, is fairly toxic to the human body, especially in the quantities we as a current society eat it in, more so in high gross domestic product countries. Carbohydrates, they get a good and bad rap all the time. They're good for you, they're bad for you, they're good for you, they're bad for you. You have all these low carb diets, which basically actually, I've done a low carb diet once in my life a couple of years ago. I was really into working out and exercising. I lost 28 pounds in 3 months. So clearly my body had some weight to lose. And what low carb diets do is it takes the amount of carbs you eat and narrows it down to only 5 to 20 milligrams of carbs a day. You have to really keep track. It's basically excessive starvation in terms of energy, and it makes your body have to turn to the fats that you have stored in your body and break them down. It takes more energy to break down fats, and you get less energy out of a broken down fat. And so your body is just using up all of its stored energy instead of quick energy from food. It can be harmful for your liver. It can be bad for your kidneys because you're processing so many proteins. They're called ketones that you produce from breaking down fat. But short term, it does jumpstart weight loss. It's definitely not something you're supposed to do long term, but they're energy molecules. That's what carbs are. Carbohydrates are composed of carbon, hydrogen and oxygen, or water. So it's a carbohydrate or hydrate. Somehow you have to roll that R from one to the other. The formula for carbohydrate is CH2O, and then multiplied by however many C's that you have. And so our normal glucose sugar, the most common sugar that we ingest, is C6H12O6. The function is energy storage. If you eat too many carbs, they then get stored as glycogen in the liver. These are raw materials. The carbon and the hydrogen and the oxygen end up being raw materials for building proteins or bone structure or tissues, and then they can be structural as well. The monomer for carbohydrates are simple sugars. When you put a whole bunch of simple sugars together by dehydration synthesis, then you get a polymer of carbohydrates. Our polymers of carbohydrates in nature are starch in plants and glycogen in animal fat. Well, no, not in animal fat, in animal tissue. Sorry, because fat is fat. Most names for sugars end in ose: glucose, fructose, sucrose, maltose, all those. It's classified by the number of carbons. So C6 is a hexose because you form a hexose ring. You know, you have 6 sides to it, a hexagon, so it's a hexose. And that's our glucose. You can have 5 carbons, which are pentose. The most classic example I can give you for a 5 carbon, a pentose, is in DNA, actually, which will be our last topic of this section. But DNA is made of a phosphate, a ribose sugar, and then then a nucleic acid base. There's a ribose. We obviously lose a carbon, right? It's 6 carbons and 5 carbons, and the structure changes as well. And then you can have trioses or glyceraldehyde. This is actually an amino acid when combined. This is an amino acid side group. So when it's combined to a carboxylic and an amine group and another hydrogen, that's an amino acid. Sugars contain carbonyls. Remember those functional groups. Please remember those functional groups. You need to know them. Carbonyls, remember, if they fall at the end, they are aldoses. And if they fall in the middle, they are ketoses. So the functional group of carbonyls, and then of course, you have hydroxyl groups all around the sugars. You'll see in the video that you have to watch, Mr. Bozeman, no, that's not it, Mr. Anderson from Bozeman Science explains that these hydroxyl groups and that carbonyl, give it partial negative charges, and also load it up with energy. It's full of energy because of these functional groups that are attached to it. So as we break the bonds to break down sugar, you release large amounts of energy. In nature, things don't tend to be linear like this structure right here. In nature, especially in aqueous environments, things tend to form ring forms. When you get into organic chemistry in college, you will be responsible for understanding how to turn a linear form into a ring form. But the gist of it is you count the carbons, you fold a carbon around to the other carbon, and then you can have all the additional atoms or groups of atoms shown that come off of each individual carbon, or you can abbreviate it slightly, which, sure, that's apparently because they don't have the carbons. You don't sew the carbons. Every point, this is actually kind of important. Go here. Every point that is not labeled on a hexose or ribose, it is a carbon. They don't have to label the carbons. The oxygen is labeled to let you know that is not a carbon, but everything else is automatically assumed to be a carbon. So that's organic chemistry. Well, here, we'll just go back. So you form bonds, you make the hexose structure. 5 carbons and 6 carbons sugars form rings in solution. And if we were in class, I would ask you, where do you find solutions in biology? And you would say, anywhere in the human body. And we'd be like, yes, because we live in an aqueous environment, yay. Carbons are numbered. That's an oxygen, it's not numbered. Coming off the oxygen, you have C1, C2, C3 right here, C4, C5, and then C6 is actually sticking up in solution. And the energy in this structure is stored in the bond. Dehydration synthesis, you make bonds, energy is stored in the bond. Hydrolysis reactions, you break bonds, energy is released from the bonds. We have simple and complex sugars. You have monosaccharides, simple one monomer sugars. There's like 6 of them, but our most common one is glucose. Disaccharides are 2 monomers. Sucrose is 2 glucose together. And then polysaccharides are large polymers, and this is starch in plants and glycogen in animals. As we said, you do dehydration synthesis to make the bonds. This is important, and I want you to maybe in your notes make a little chart, because the name for all the bonds that we make are different. So for carbs, what we end up making is something called a glycosidic linkage. There it is. So we take 2, oh, look at me, I was wrong. Maltose is 2 glucose monomers, which means sucrose has to be glucose and fructose then. Interesting. Anyway, maltose, you know maltose. Maltose is in malted milk. It's in malted milk balls, which used to be a Halloween candy that I hated. So, I mean, they're around beyond Halloween, but people would put them in your little trick-or-treat things, and I never liked malted milk balls, but I do like malted milk shakes. Or at least I did 10 years ago when I was serving them in a diner. But maltose is a milk product. Let's just say that. So you take 2 glucose monomers, you do a dehydration synthesis, you lose water, you form a bond between them, and it's called a glycosidic linkage. And for fats or lipids, it has a different name. For proteins, it has a different name. And for nucleic acids, it has a different name. They're all done by dehydration synthesis, but we have different names. And you use maltose in alcohol, apparently. And here we have glucose and fructose. Oh, let's see if I'm right. Yes, and we get sucrose out of that. And so fructose is natural sugar found in fruit. It's the sugar you're supposed to want to eat. If we didn't have processed sugar as an option, fructose would be our only real option for natural sugar, and you would all be gorging on fruit, which would be fantastic for your health, because when you eat whole fruit, you also eat the fiber. And so whole fruit, fructose itself can lead to weight gain, but the fiber content in the fruit actually mitigates those effects, because it's cleaning you out and keeping you regular, and you're not holding in waste products that can then be stored. So you're always supposed to eat whole fruit, I say. And then what we tend to do, however, is eat a whole bunch of not whole fruit sugar, like cookies, like lemon cookies that I made this week, and I've eaten so many of them. Polysaccharides are polymers of sugar. It costs a little energy to build. They're easily reversible to release energy. The function is energy storage. We starch in plants, carrots, potatoes, anything that's like an underground tuber, pretty much, and glycogen in animals, in the liver and the muscles. We don't store it like, no, I'm sorry. I'm saying it wrong. So it's starch in plants and glycogen in animals. That's how we store it. But then we can use it in structures as well. And so chitin in insects and fungi, arthropods and fungi, chitin is that hard outer shell. I'm not shitting you, it's pronounced chitin, okay, with a hard K sound. And the shell of crustaceans as well. Cellulose is the plant structure. Have you ever eaten celery? I'm assuming that all of you have probably eaten celery at least once in your life. And if you can remember, when you bite into it, you get all these like stringy bits that don't bite through, and you like pull the celery out and you get all these stringy bits. That's cellulose. Cellulose is indigestible in human bodies, so it's great for fiber, but also gets stuck in your teeth, and that's really annoying when you eat celery. We store long chains of polymers, and they can be linear and straight long chains, or they can be branched polymers. And branched will take more energy to break down than linear. But branched is actually more effective to break down, and I'll show you why in a minute. So starch products can be amylose or amylopectin. Here is some starch in a chloroplast of some plant. And then glycogen is actually heavily branched in animal muscles and liver. The reason branching is effective for us is that you can store more if you branch, but also you can break it down faster if it's branched, because you can have enzymes working on this, on this, on this, on this, on any of the ends that are free. An enzyme can start breaking it down. So you can have many enzymes breaking it down as fast as they can at each branched end. If you're just a long chain, you can only have 2 enzymes working on that chain, one from each end to break it down. The molecular structure of anything determines its function. So you can have isomers again. Remember, isomers are same structural equation, different actual structures. So sorry, it's 7:45. Different AM. Different actual structures, and structure determines function. So we have alpha glucose and we have beta glucose. This determines if it's something we can digest or we can't. We can digest starch, we can digest sugar, we cannot digest cellulose. And it depends on if that glycosidic linkage forms down or forms up. We only have one enzyme. Oh, sorry, we'll go back so you can see what that's, we will go back so you can see what that says at the very end. So in starch, we can break down, we have alpha linkages. In cellulose, we can't break down, we have beta linkages. And when I say linkages, I mean glycosidic linkages. So starch is easy for us to digest. We have enzymes that recognize that alpha glycosidic linkage, and it just breaks it apart with hydrolysis, and we release energy and we use it. Cellulose, we barely digest. Our enzymes don't recognize that beta glycosidic linkage. So watch the enzyme. It tries, but then it goes on with its life because it just doesn't recognize it. So you don't digest cellulose, which means that you poop it out, which is great. It's fiber. That's what cellulose is. And so you're supposed to have high fiber diets to keep yourself regular. And if you ever wonder if you're healthy, just record how much you defecate in a week. If you're doing it daily or more than once a day, that it's normal solid stool and not diarrhea, then you're healthy. If you are defecating like once a week and it's difficult for you to go, then you need more fiber in your diet and probably more water as well. I know it's not kosher to talk about defecating, but it is very important to your health. You can tell massive amounts of information from people, and doctors do this by their height, weight ratio, by the last time they pooped and what the structure of that poop was like, and the temperature, pulse, and respiration. That's why they do vitals when you go into your doctor's office, even if you're not there for anything you think the vitals matter for, because that tells you so much information about that individual. Cellulose in plants, it's the most abundant organic compound on Earth, and herbivores have evolved a mechanism to digest cellulose. Herbivores typically have multiple chambers of stomachs. Our cows have 4 stomachs. They're not 4 full stomachs. Each stomach does a different function. And then cows regurgitate, swallow again after they chewed it up some more. And they have evolved this mechanism with the use of bacteria in their gut to break down cellulose. It's very energy taxing. It's not very efficient in terms of getting energy, but that is the mechanism that evolved. Most carnivores, which we're omnivores, let's get it straight. We are not straight carnivores, but like lions and cheetahs and bears, oh my. Although bears are actually not straight carnivores either. They'll eat berries and nuts and anything else that they can find. But straight carnivores have not evolved a mechanism to digest cellulose, and that's why they eat meat, because glycogen in muscle tissue and livers super easy to digest. So for carnivores, cellulose becomes undigestible roughage or fiber, which we've talked about. So talking about that cow and these gorillas, they can digest the cellulose wall. It takes them forever to do it. That's why they're constantly grazing. Cows can't really stop eating except to sleep, because it takes so much for them to be able to get enough energy out of what they eat. Gorillas can't digest the cellulose wall. We're not from gorillas, we're from chimpanzees, but whatever. But we're like gorillas. And so they must add another sugar source like fruit to the diet, like we do. So here is a cow. Look, they have 1, 2, where's 3? Oh, because they regurgitated 3. But okay, so regurgitating doesn't really count. They have 1, 2, 3, 4 chambers to their stomach to help them break it down. Bacteria live in their digestive systems and help digest this cellulose-rich meal. And so they swallow, okay, so they chew forever, and then they swallow it the first time into the rumen. And it's broken down a little bit in the rumen, and then it goes into the reticulum, where a whole bunch of bacteria live, and they work to break it down. But then they regurgitate it again and chew it again. It's called chewing their cud. Your cows just sit there and chew and stare at you. If you've ever experienced cows, if you've ever gone out of the city. Then they have to swallow it again. It goes to the omasum, I assume is what it's called. And then eventually it hits the abomasum, where final digestion occurs into the intestines. We also have animals called coprophages. Caprophages, excuse me, I don't say things right. Coprophages, Copacabana, dun, 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 dun. Okay, y'all don't need that. Caprophages eat poop. Other people's poop, maybe not people's, but other animals' poop in terms of flies. They secrete digestive enzymes on the poop structure and then suck it back up. That sounds absolutely disgusting to us, but you have to know that anytime an animal defecates, typically there are a ton of nutrients left in the waste. So other animals have evolved means to get those nutrients out of the waste. And then rabbits actually have 2 different types of poop. Oh, sorry. And what they do is they have a very solid, hard pellet poop. It's the normal possible rabbit poop that you've seen. And then they have a very soft second poop. That hard pellet poop of rabbits is actually half digested material. And so they have to re-eat it to get full digestion, to get full nutrients out of their hay and food if they're pet rabbits, or out of whatever they're eating in the wild if they're wild rabbits. Sounds disgusting to us, but it is a mechanism to get nutrients. So I have never probably noticed this little girl, or yeah, I think girl in the background here, because you're so focused on the one eating the little piece of bread. I think it's bread. Carbohydrates, we love them as a species. It's our favorite thing. We use them for simple energy. They come in forms of monomers, disaccharides, which means 2, and then long polymers, either chained or branched long polymers. We can break down alpha glycosidic linkages, but we can't break down beta glycosidic linkages. And while I agree with all of you that carbs are fantastic, everything in moderation. It's not supposed to be the only thing we eat. Thank you.